science today, chapter 3. And before we get into that, you guys know we're going to run down the list of announcements. And so the biggest announcement is that exam 1 is a week from today. So it's here, it's upon us. I have lots of work to do today after our lecture. So I'm going to be sending some info. I'll be posting some stuff in Blackboard this evening, extra practice problems to work. I think hopefully it should work out that we have time to do some review on Thursday before exam 1. I'm also going to start, maybe even try to make it a weekly thing, but I'm going to send out a poll about what time would be best on Wednesday or Friday. Just Tuesdays and Thursdays are no good for me with all the lectures that we do. So Wednesdays or Fridays, I may try to offer like a 1-hour Q&A session time and create a separate Zoom link for that. People can jump on if it works for them and ask questions. You can still always set up an individual Zoom with me. So don't feel left out if you can't go to those depending on what time they end up being, because you can always email me. I had two individual Zoom meets with students this morning, and I think hopefully they went well. So some of you are doing that. If you feel like you're stuck or you have questions or you're lost, you're reaching out, and I commend you for that. Some of you, we're going to find out if you're lost or not next Tuesday after the exam. So when will the labs be graded? The questions are coming in. I told you I have a lot of work left to do today, so I'm gonna start. I didn't do any work over Labor Day weekend. I bet you guys didn't really either. We decided it was the perfect weekend to re-landscape our entire front yard, and it actually was nice outside. So, do we have lab? No lab this week. No lab this week, but I have your labs to grade from last week, so I'll be getting those graded this week, and I will have them all graded before exam 1, because then I will start grading your exams. The format of the exam is so question for that first one, they will be graded throughout the week. So hopefully by the end of the weekend, everybody's labs will be graded. And then exam 1, here's the format. It'll be on Blackboard, and I usually have about 10 multiple choice questions. Oh, there is a rush, Tierra, because I don't want to have to grade your labs and your exams all at the same time. So yes, there is a rush to get those done, right? So the exam format, roughly 10 multiple choice, okay? Then there'll be some other questions. There'll be a complex conversion problem or 2 or 3. There will be temperature conversion problem, specific heat problem. So categorizing matter, all kinds of things. We'll go over list review stuff. So somebody asked me how many questions are on exam, and that's really a hard thing to answer. There's less than 20, but some of them have like part A, B, and C. Okay, so that's kind of an idea of the format. The way it'll work is I'll open the exam up at 8 a.m. on Tuesday, and you'll have all day to take it. But once you start it, you'll have like an hour and a half to finish it. I'm not going to give you 3 hours to take it because I feel like you either know the material or you don't. And I will also, be encouraging everybody, make sure it's very easy, especially if you don't have your video turned on, which I'm not requiring you to turn your video on. It helps me. I love seeing your faces. But if you don't, it's very easy for you to just have me playing over in a corner of your dorm room. And I don't know if you're listening or not. So for those of you who may not be engaging, that may be detrimental to you on an exam. So I want you to attend. I'm making attendance mandatory, but I have no idea. This is the first time I've done online lectures, first time for y'all probably too, the level of engagement. I don't know how easy or difficult it is on your side to engage via a screen. It could be very easy to check out, I'm sure. And so I just want to encourage you guys this semester. I feel for you guys because it takes way more self-discipline than other students sitting in a lecture hall with accountability around you, people staring, and we're all listening. We're in a room together. It's probably easier to engage that way than it is here. So I've gotten some feedback from one of the discussion board questions that I asked. I wanted to learn a little bit about you, and somebody mentioned please do more polls because they help me engage. And so I failed the 1050 lecture because I had Zooms this morning with students. And so I didn't get the polls done, but I have polls for you guys today. So hopefully that will help you with engaging. But all that to say, Oh, I'm here, I promise. Okay. Well, at least I know some of you are here. Again, I'm not saying that you're not engaging. I know it's got to be challenging. And so I want you guys to do all of these exams. I'm going to try to explain things and talk through things as best as possible. But I know I'm sure it's probably difficult via a screen all the time, all day long, so on and so forth. So, all that to be said, that's the biggest announcement. The other announcement is that your Chapter 3 homework is available on Mastering as of 9 a.m. this morning. So you can begin working on that. When is it due? Midnight before the exam next week. So next Monday night at midnight it's due, 11:59. And then what else? What other announcements? No labs this week. So that's kind of nice because it allows you to focus on the exam and prepping for that. And any other announcements? I think that's it. Last time, as I'm updating our attendance sheets, I still see people that are like, their name is logged on as A. You're the letter A, and I have no idea who you are. So if you're the letter A, please change that because I don't know who to give attendance to. And I'm also going to be, as I'm realizing, if I have 2 or 3 absences for you on attendance, I'm going to be sending out emails because, hey, warning, I start taking points off with it, like absence number 4. And if that is messed up for some reason, like you're like, hey, remember I told you that my tornado siren was going off in my dorm that one time and I couldn't attend. Just remind me, okay? If something's off, I want a dialogue. I'm just gonna let you know where I have you for attendance. And I'm not gonna be sending out emails to everybody if you've attended and I have that, like all 4 or 5 lectures we've had so far. But if I have absences for you, like 2 or 3, I'm gonna be trying to send you an email in the next week or so saying, hey, this is what I have. And if you think that's not correct, let's talk about it, okay? All right, that's all the announcements I have. And I wish I could say enough of me talking, but here we go. I'm going to share screen and we're going to get into chapter 3. Remember, you should be reading the textbook with this. So the assigned reading were the first couple sections of chapter 3. If you have not done that, please get on that as well. It should help you prepare for the exam. All right. But the last fun thing we'll talk about before we lecture, which I think is still fun stuff. But here is the picture for the week, Horseshoe Bend. I would love to know, let me pull the chat up, if anybody's actually been to Horseshoe Bend. This is part of the Grand Canyon trip that we went on. This is, I think, the last picture I have of the Grand Canyon trip, and then I'll show other hiking pictures starting with next week. But this is about an hour-and-a-half drive from where you can camp on the South Rim, like the national park you can camp in. So you got to drive here, and it kind of is weird. You like, it does not feel like you're pulling up to anything. It feels like you're in the middle of nowhere, and you literally park in this, I don't remember if the parking lot is like gravel maybe, and then there's just like sand dunes, and you just walk over this sand dune, and then voila, this beautiful piece of rock is here. And then there's people everywhere, but you can't see it from the road, so it's really weird. But we got here and you kind of walk down a little bit of ways and you can see it the whole time. This is beautiful. It's called Horseshoe Bend, and you can see why, because the river flows around this piece of rock and it creates a horseshoe. Obviously with my camera, I just don't have a high quality enough camera to get everything. So if you have a really high quality camera, take it. You need like a wide angle lens to get everything. But there's no rails at the same time to keep you from falling off the edge and to your death. So please be careful if you go. There are people sitting on the edge, throwing their feet over the edge. That was not me. My husband wanted to like lay down and get as close as possible to the edge as like he could, and I was like, no thanks. You can get that picture by yourself. But this was a really, really awesome place to visit. And if you want to like stay a couple days and do multiple hikes, but give yourself a day of rest in between some hikes at the Grand Canyon, this is a great thing to do in between those hikes because you're mostly driving there and back. Okay, let's talk about chapter 3, chemical bonds. So we've talked about matter and different properties of matter and measuring matter and converting between those measurements. We have talked about atoms, and we have talked about valence electrons and subatomic particles and how atoms are arranged. And if you remember, we said atoms, they all want to be stable. They want to be in the most stable state possible. Okay, and that's actually our first point. Is that everything in nature desires to be in the most, stable, I'm not on my pencil, there it is, state possible, okay? Now, some elements, could anybody tell me an element that's already actually very stable? We mentioned this last week. What are some elements that we know are already stable as is?
Neon?
Neon. And neon is part of what group?
Halogens?
No.
The
Noble gases.
Noble gases. Thank you. The noble gases are already stable. Why are they stable? We said there's something magical about the number of valence electrons they have.
they have 8.
Yes, they have 8 valence electrons, which makes them incredibly stable. And all other atoms, therefore, want to be like the noble gases. They want to have 8. The problem is they don't. So they're going to do some things to get there, and we're going to talk about what they're going to do. And those things are going to result in chemical bonds, okay? So what is a chemical bond? It is the direct result between the electrical attraction of opposite charges. Okay, so I have this cute picture over here in this yellow box. That it explains that to you. It's a positive and a negative charge that are attracted. And what things in an atom did we say have positive and negative charges?
Protons and electrons.
Yes, protons and electrons. Now, the picture below that is actually the one I want to talk about. It's a little more technical. Because there's 2 types of chemical bonds, by the way. And we're going to talk about one kind today. There's 2 kinds. I'm gonna write them up here. The first kind is called ionic bonds. That's what we're going to talk about today. The second kind is called covalent. I'm not sure I told the morning people this. I hate it when I do that. I wish they could be the exact same lectures, but I'm human. So we're going to talk about ionic bonds today. All right. And what is an ionic bond? They're the basis of this word down here, ionic compounds. This is how they form. And essentially in this picture, this is how an ionic bond is formed. An electron is traded from one atom to another. Okay, that's what an ionic bond is. An electron is traded from one atom to another. Okay, with nothing in return. So I don't know if you want to use the word traded, but an atom is given from one atom to another. And that's what you see. Okay, you can see the proton, the nucleus, where the protons are in each of these atoms. And both atoms have 2 energy shells, the one on the left and the one on the right. But each of these elements have different number of valence electrons. The one on the left has 1 valence electron, right? And the one on the right has 1, 2, 3, 4, 5, 6, has 7 valence electrons. So what's going to happen for these both to become, neither one is as stable as they could be, okay? Because underneath on this atom on the left here, underneath, it has a full set of 2 valence electrons. Remember, that first energy shell can only hold 2 valence electrons. So if atom on the left decides to give away its electron, it could have a full set underneath, and that's stable. If the atom on the right gains 1 electron, now it will have 8 valence, and it will be stable. So when these atoms bump into each other, they sign the contract. They're both happy to make that trade and participate in this deal. An electron is given, that's what this arrow indicates, from the atom on the left to the atom on the right. All right, and that's what forms a chemical bond. In this case, it's an ionic bond. Why? Because what's left over after that electron is given are what we call ions. And we haven't even talked about what an ion is, but we're going to explain what ions are in a minute, okay? All right, so what is an ionic compound? It's a compound that forms between 2 ions, okay? When an electron is completely given or completely received, or sometimes more than 1 electron. Here's an example of an ionic compound. We said last week that the group 7 elements, when they react with the group 1 elements, they form salts. We say their compounds are commonly called salts. And here is salt, sodium chloride, all right? So this is salt, NaCl. And you also see the 2 elements, the 2 reactants that form salt, okay? So we saw sodium metal react with water last week. We know it's this shiny metal down here. Okay, there's sodium. So what's in the gas? That means the gas is, or this bottle. It's chlorine, right? It's kind of a greenish color. Chlorine is a toxic gas in this bottle. Now, a picture on the right is those 2 things reacting. So in that beaker, we introduced chlorine gas. and sodium metal. We put them together. And look at this, guys. I mean, that's fire and smoke. And these things react violently, okay? And this is all due to what? It's all due to this, an electron jumping ship from one atom to another. But it's happening millions and millions of times because, you know, atoms are really, really small. And so there's a lot of atoms in that beaker. So this kind of reaction is due to the fact that electrons are being traded. And then it forms this very edible, docile, what we call ionic compound. We call ionic compounds, we call things that trade electrons ionic compounds, and they form ionic bonds. Hold on, sorry, I had a message I need to respond to. Just a second on the chat. Sorry, everyone. Oh, guys, I'm new at Zoom. I don't know how to respond to this person privately, and they're asking me a question. All right, that should work. Okay. So speaking of ions, ionic compounds, why do we care about ions? Why are they important? Well, they're very important for a lot of reasons. And the first reason, just to be a little bit relevant, is electrolytes. We call ions, a lot of you know them as electrolytes. And can we pause and remember, we knew this year was going to be crazy when it started off with the fact that Kobe Bryant died. Okay, that was the first sign that 2020 was going to be a crazy year, right? Maybe you haven't forgotten. But he had his own line of body armor drinks. Okay, it's what they're called, body armor. Sports drinks is what you should call them. And it's kind of like Gatorade, Powerade. And I was actually comparing his line. I've never had one of his products. Maybe I teach about them, so maybe I should drink one. His are supposed to be healthier than, say, your Gatorade as a comparison. If you look at the amount of sugar, okay, there's 18 grams of sugar in a cup, 8 fluid ounces, which is like half of what Gatorade has, okay? Last time I checked, at least. Maybe Gatorade's gotten better. And then they also have, look at the electrolytes, 700 milligrams of potassium, which is way better than Gatorade. And then it also has less sodium than Gatorade, okay? And some people, you know, want to watch their sodium intake as well. So these are all great things, plus a ton of different vitamins. So his drinks are supposed to be very good for you if you want to try them. Powerade also is another type of sports drink that you'll drink, you know, to intake electrolytes. And so I'm talking about all these electrolytes, but why? What do electrolytes help us do? When do we need them?
Something about not being dehydrated.
Yes. Okay. Was somebody else saying something too? Dehydration?
Yeah.
Okay, I thought somebody, okay. So dehydration, when you're going to become dehydrated, what happens to your body when you begin to feel dehydrated? What are some of the symptoms you can feel with that?
Fatigue.
Fatigue is one.
Dry mouth.
Dry mouth, a headache.
You start sweating.
You can
Stomach cramps.
Stomach cramps, nauseous. There's so many different things. Like, you do not want to be dehydrated, okay? And I know we've had a really hot summer here in Arkansas. Weather's starting to cool off, so that should help some. But that is why we need electrolytes, to help keep our body balanced and hydrated, okay? Now, there's other critical biological roles besides those things that electrolytes do for us. So we're going to look at what these are. Other biological roles. So, by the way, for the exam, I'm going to kind of blaze through this slide, but this is a really important slide. I want you to be able to tell me some of the roles of ions, aka electrolytes, on the exam if I were to ask you, okay? So let's look at sodium. What all does sodium do? Well, many of these ions you'll find overlap. They have similar roles and responsibilities that they share. A lot of them can be regulating osmotic pressure and our water content. Again, that's hydration. But look here, nerve transmission, okay? We could not send our whole nervous system would not function without sodium or potassium, okay? Those are both critical ions when it comes to our nervous system firing properly, okay? You'll see a lot of ions play a role in muscle contraction, all right? So you see that with sodium, certainly, and again, over here with potassium. And then what else? Let's look over at magnesium. Again, muscle contraction, but magnesium as well as calcium are important for our bone and teeth formation. You know calcium is important for, you start learning that when you're like a kid, for bone formation. And then chlorine has a unique role. We know hydrochloric acid is what our stomach acid is. So chlorine is helps enable the secretion of our stomach acid as well. So those are just some of the roles that ions play that are very, very important. So not only do they keep us hydrated, they play they do these other biological roles in our body. But here's another important thing. What do you guys see on this slide? Oh, do
I
need to go
can't
back to
see
that?
what you're writing. Or if you're writing something, I can't see it. Like, I just see your face.
You don't see my screen?
No,
Like the lecture slides?
no.
Okay, why don't I do this? I'm gonna stop share. Now you can see my face. I'm gonna reshare.
Thank you. I see now.
See it now? Okay. Let's scroll on down to this slide. Is that okay? Everybody with me? Okay. What do we see here? What's on this slide?
Looks like oxygen, O2.
Yep,
red blood cell?
oxygen. A red blood cell. Okay. Chat. Red blood cell. Okay. Yes. And what you see, it's kind of the cartoon picture, but these green, different shades of green looking things, this is hemoglobin. Okay. So it's a very cartoon picture, but hemoglobin has 4 places that oxygen can bind to it. And hemoglobin is the protein or the enzyme in our red blood cells that's responsible for transporting oxygen to every cell in your body. So hemoglobin is really important. And I want to zoom in on hemoglobin because you'll see in every location where we bind oxygen, what do you also see?
Iron.
Iron. You see an iron ion, okay? An ion of iron. So again, we'll define what an ion is in a minute. I just want to show you the importance of this. We could not transport oxygen to any location in our body without ions, specifically iron. Now, the reason our blood is red is because of iron. Iron is also what colors red meat a lot. There's a lot of iron in red meat. And then rust, is a red color. So iron, that's why it's red there. But ion is important for oxygen transport. And I'm going to show you one more example why you should care about ions. They're used in all kinds of commercial products. I'm just going to show you one. Toothpaste, okay? My sister is a dental hygienist, so guess how many times a year I get asked if I'm flossing? You only get asked twice a year. I get asked like every day if I'm flossing, okay? Don't tell her that I don't floss every day. But I have a Sonicare, so I do brush my teeth. Anybody ever left your house before without brushing your teeth? Is that not like you walk out and you're like, oh crap, I forgot to brush my teeth? That's the worst feeling in the world. Probably even feels worse than making a bad grade on your exam next week. So just brush your teeth, all right? But look here, we have this fluoride ion, all right, in toothpaste. They're in all kinds of products that we use, and they serve purposes. Here, it helps against cavity protection, all right? Helps with the enamel on your teeth. So that's why we should care about ions. They're incredibly important. Now, what is an ion? I'm going to give you kind of a really technical definition, but for a purpose. So we've seen this picture on the left, and we see how the electron's being traded. But what happens to an atom when an electron is traded, okay? So an ion is an atom that has either lost or gained a valence electron and is therefore no longer electrically neutral. I told you this was really technical, okay? We said last week that atoms have the same number of protons that they do electrons. We said the role of a proton is to balance the number of electrons, and the role of an electron is to balance the number of protons. Therefore, atoms are what we call electrically neutral. Charge-wise, they carry 0 charge. But it changes now that we have ions, okay? An ion is not electrically neutral because the balance between the protons and electrons has been broken. They're not balanced anymore. So let's think about this. Here's this kind of diagram I want to walk through. We have a neutral atom starting out. If we give away an electron, okay, if we lose an electron, so we're going to follow this figure to the left. We end up, the kind of ion that we have is called a cation. All right, now I can't take claim for what I'm about to say because someone that's really brilliant from the first lecture said this. Cats have paws, right? You guys know that. Cats have paws. Cations, therefore, when they lose an electron, they're positively charged. Get it? You're welcome. You're going to remember that on the exam now because I said that. Cats have paws. Cations are positively charged because overall, we don't change the number of protons. We change the number of electrons. We've lost an electron. So let's do a little thought experiment. If we have an atom with 10, starting out, it has 10 protons and 10 electrons. Let's say we lose one electron, so minus one electron. Now how many electrons do we have? We have 9. We still have 10 protons. Okay, so this was minus 0. So we still have 10 protons, and these are positive charges. 9 electrons and 10. So essentially we're saying a positive 10 plus what? A negative 9. Let's do that math. That's the math here because protons are positive, electrons are negative. What do we end up with? We end up with a positive 1. Okay, we call that a cation. Cats have paws, everyone. Okay. All right, let's follow this diagram the other way. We have a neutral atom again. We're going to do the same thing. 10 protons, 10 electrons. What if we gain an electron? What do we end up with? So now we're going to say plus 1 electron, okay? Because this atom over here on the right is gaining. The atom on the left lost. So now we have 11 electrons. We still have 10 protons. So we have positive 10 plus negative 11. That gives us negative 1 overall. We call a negatively charged atom an anion. Okay, I don't have a fun, anybody have a fun one for anion that we can remember it by? Now's your chance. I guarantee you if I was like 1 bonus point, someone would come up with something. But okay, so we call negatively charged atoms an anion, positively charged atoms a cation. And it's all due, we didn't change the number of protons, all due to electrons, movement of electrons, okay? Questions so far on ions? Okay. We're gonna continue to look at this, but from a little bit of a different style of picture. You guys have seen me draw the layers of the onion around the nucleus, okay? And remember, we call those onion layers. I learned that anions are like ants with the shape of them. Okay, explain. We've got something interesting going on in the chat here. What do you mean? You can either unmute yourself and chat or...
So my chemistry teacher used to refer to them as ants because like the shape of them, they just look like a bar. And so since anions are like negative.
So yeah. Like, I'm gonna draw an ant. You guys wanna see my ant drawing? Here's an ant, right?
Yeah.
Is this a good ant? Thank you guys. Okay, continue. So it looks like a bar, right? Because they're long and horizontal.
Mm-hmm.
So it's a minus.
Yeah. So that's
okay.
Not, like that's a trick that you can remember that anions are negative, I guess.
That's free wisdom from Dakota, everybody. Thank you, Dakota. Okay. All right. So we have cats have paws and anions are ants. There you go. I really do love this stuff. Believe it or not, even if you think it's stupid, it will help you memorize it. I promise. You know that's true. Okay, layers of the onion. First off, I want you to ignore all this 3s1, 2p6, blah, blah, blah. If we were getting into electron configurations, we would talk about that. And if you were headed like to Gen Chem 2, you would need to know this stuff. But most of you, that's not the case. So even if you've seen it before, just don't worry about it. So we have this picture. We're going to talk about a sodium atom. Okay, because earlier on we talked about sodium chloride. We have sodium and chlorine. Let's look. We saw the reaction in a beaker and how it had like fire and smoke, and it was fun to look at. But let's talk about what's happening with the electrons. So here's an atom of sodium, and we have 11 protons in the nucleus. And we have 11 electrons across the 3 shells. Let's count them. We have 2 in the first shell. We have a full set of 8 in the second layer. We have 1 valence electron. So what group is sodium in? Do you guys remember how to count valence electrons? It matches the main group number, right? So if we have 1 valence electron, sodium's in main group 1, okay? So total, when you add all those electrons up, we have 11. And everything's balanced, everything's neutral. Now, sodium, to become stable, okay, to have 8 valence, the easiest way for sodium to do that, you could add 7 electrons to this outer shell, but that's a lot of work. Or, that's too much work. Or you can lose this 1 electron on the outer shell and look underneath. That second layer now becomes the outer layer because the third shell disappears. If there's no electrons, you don't have a third shell. You only have a shell there if there's electrons in it, okay? So now we have a full set of 8. Sodium is way more stable, way more satisfied, is happy to get rid of that electron. But now look at the imbalance, 11 protons, 10 electrons. So we have a +1 charge overall. When you write ions, you write the symbol and you now write the charge. It is critical that you write the charge. If you just told me sodium, that's not an ion, okay? This is a really small thing here, but it's really technical. And it matters that you write the charge. And when you're memorizing your polyatomic ions, you have to know the charge associated with each polyatomic, okay? So that is sodium. Let's look at it from chlorine standpoint, chlorine perspective. Chlorine has 17 protons in the nucleus, 17 electrons as well, because we've got 2 on that innermost shell. Remember that first layer on the onion. Here's the nucleus, here's the first shell. That can only hold 2 electrons, okay? So that's why you're always just going to see 2 on that first circle around the nucleus. The second layer can hold 8 electrons. And then we find in the third layer that there's 7. Okay, so chlorine has 7, how many valence? 7 valence electrons, which it's in main group 7. What do we call main group 7?
Halogens.
There you go, Janelle, the halogens. Okay, so the quickest way for chlorine to become stable like a noble gas, we need to add 1 electron. So if it gains 1 from an element that's happy to get rid of 1, like sodium, now we have 8, okay? And then because there's now an imbalance between the protons and the electrons, when you add up 17, a positive 17, each proton has a positive, plus a negative 18, each electron has a negative, that equals -1. So that's why we write chlorine with a -1 sign. And it's very important that you write it as a superscript. Okay, the charges are written as superscripts. Okay. Also, I want to point out something I forgot to say. Notice when we went with sodium that we lost that 1 electron. Well, now we only have 2 layers around the nucleus. We only have 2 shells instead of 3. And what that means is that the atom is actually physically a little smaller. Okay, so I'm going to make a note here because cations tend to be smaller than their neutral atom. Okay. Cations tend to be a little smaller, so guess what? Anions
Are
10.
bigger.
do what?
Are bigger.
Yes, they tend to be bigger. You're catching on, everyone. Okay. Let's keep moving. We're going to pause on these diagrams for a second, and I'm going to introduce 2 properties because here's the deal. We've only talked about 2 elements. I want you guys to know this stuff, and once you learn it enough, you can predict what almost any element on the periodic table, what kind of charge it would have as an ion. Okay? The only elements you're not going to do that for are the noble gases. They're not going to form ions. But any other element, I'm going to show you from understanding what we're going to talk about, these next 2 properties, you can predict. You can look at any element and say, okay, that's going to be an anion with a -2 charge, or that's going to be a cation with a +2 charge. Okay, you're going to be able to do that. At least I want you to be able to do that. So let's talk about these two properties really quick. When we're forming ions, here's kind of some general principles that they abide by from these properties. The first one is called ionization energy. What is ionization energy? It is the amount of energy required, okay, or added, in other words, for an atom to lose a valence electron. Okay, so some elements, like we saw with sodium, they tend to give electrons away. Sodium does not want to accept electrons. Some elements, like chlorine and the halogens, they tend to receive electrons. So different elements behave different ways. We're going to figure out why that is. It depends on their number of valence electrons and therefore their placement on the periodic table. But here's ionization energy. So look at this kind of schematic. By the way, this is figure 3.2 in your textbook if you want to go back and look at it. What we're saying here is that we have a neutral atom. If we give it enough energy, pay it enough, eventually it will give up an outer electron, okay? And then you'll have a cation and you'll have a lone electron that'll probably be picked up by some other atom, all right? So for an element to give up an electron, you have to pay it some energy. You have to deposit or invest some energy, okay? It's all about energy here. Electron affinity, that's the other property. Now, what does that word affinity mean? If I tell you I have a very high affinity for coffee, for ice cream, you know I like those things a lot, and they're both true. Okay, what is electron affinity? It's the amount of energy released when an atom gains a valence electron. Okay, so atoms have different affinities for electrons. Some atoms really want one. They have a high electron affinity. Atoms that do not want to receive an electron, sodium doesn't want to receive an electron. Sodium wants to give one away. Sodium has a very low electron affinity, okay? And remember, elements in the same group, and a group is a vertical column on the periodic table, those elements are going to tend to behave the same way. So guess what? Not just sodium, but all the group 1 elements. They have very low electron affinity. They don't want electrons. The halogens, group 7, like chlorine. We just saw that chlorine likes to get an electron. All the halogens are going to behave the same way because if they're in the same group, same vertical column, they behave the same way. All right? Okay, and the schematic here, this a little chemical reaction says if you have a neutral atom, and you're going to give it an electron. It's gaining an electron. One, you know you're going to form an anion, and it's going to release some energy, okay? Now, tell me this. If you release energy, are you more stable or less stable? What you think?
Less stable?
Okay, okay, Kanithi says more stable. Janelle says less stable. Let me tell you a little story. When we go to my husband's grandparents' house, or to sometimes to his side of the family, my family does it too, but they always try to sneak my daughter sugar. Okay, I was looking over across the plate today. My daughter had a cookie after lunch, and I was like, that's plenty of sugar. She does not need 6 cookies in one day. Okay, I look across the pool, and Nana is feeding her more cookies. Okay. And I'm like, Nana, stop it, okay? If she's ramped up, I don't want her to have that much sugar because then she's ramped up on energy, right? So if we're giving her energy, she's going to be like all over the place. So think of that when you compare this with an atom. If we're giving it energy, it's not as stable. It's high in energy. The less energy you have, the more calm and stable you are, right? So it's the same way with atoms, okay? So if you're releasing energy, you're more stable. And the more energy you release, the more favorable it is for you to gain an electron, the more stable you are. That's why we're going to see, I'm going to look at this graph here in just a second. I'm going to turn my screen sideways. What elements do you think have the highest electron affinity? Which elements do you think want an electron the most? Anybody have a guess?
Halogens,
Halogens, why?
because they have 7 valence electrons.
They're 1 away, okay? If they just get 1 more, they're there. You're absolutely right. In fact, if we look at the blue data, that's the electron affinity. If you zoom in on this, okay, the highest ones are all halogens. They all have the highest electron affinity, which means they give off the most amount of energy and they're the most stable when you give them an electron. They want an electron of all elements the most. Okay, let's talk about ionization energy. You can look at this graph. Let's look at what's at the peak. Which kind of elements are at the peak here? He, Ne, Ar, Kr. What elements are these? Do you guys recognize them?
Noble gases.
Noble gases, okay? I'm going to put a little star by these. Anything that has a star is a noble gas, right? So these are the noble gases. Why do they have the highest ionization energy? Remember, what is ionization energy? It is energy that's required for an atom to lose a valence electron. So we would have to pay an astronomical amount of energy to these elements, the noble gases, for them to lose an electron. Why are they making their price so high? They don't want to be unstable. They have 8, but yes, they have 8 valence. They don't want to give away an electron. Now they're not stable anymore. They want to keep what they have. They don't want to play with anybody, all right? So they're going to make that price really high. We got to pay them a lot of energy because they don't want to lose an electron. Okay, which elements on the other side of this, which elements have the lowest ionization energy? Which elements are happy to get rid of an electron? I'm circling them. What are these elements? Li, Na.
Group 1.
Group 1. They have 1 valence, and just as we saw with sodium, let me go back up here. Look at this. If sodium can just get rid of this 1, it has a full set of 8 underneath. And it's a happy, happy person. All right. So that's a little bit about ionization energy and electron affinity. Now we drew a trend last week with atomic radius. Okay, and we said as you go across the periodic table from left to right, the atomic radius decreases. As you go down, the atomic radius increases. We're about to do the same thing with these 2 properties, okay? All right, so let's draw our periodic table. I know, it's very good. Okay. So ionization energy, what did we just learn? As you go from left to right, what happens to ionization energy? The noble gases have the highest ionization energy, the group 1s have the lowest. So as you go from left to right, ionization energy does what? Increases.
Increase.
Thank you. All right, now let me erase a little bit because you may not be able to tell. Let's look at these group 1s a lot closer. Lithium is like right on the line. Sodium's like right on the line. Potassium's down here though. So as you start to go down the periodic table from row 1 down towards row 7, what happens to ionization energy?
Decreases.
What'd you say?
Decreases.
Decreases. Thank you. Who said that? Whoever you are, good job. All right, so there's those trends. I want you to know those trends. And then for electron affinity, we're just going to talk about the horizontal trend here. That's the one that's most obvious. As you go towards the halogens, notice we said they have the highest electron affinity. Okay, so electron affinity, EA, what happens to it as you go from left to right? It also increases. Okay, so know these trends for the exam. Okay, how could I ask this to you on exam? Here's 4 elements, and in fact, there's some practice problems in your textbook at the back of chapter 3 Remember, by the end of the day, I'm going to post a list of questions I recommend you working out of the textbook. And there's answers, I believe, to the positive ones in the very, very back of the book. There's some practice for this. Here's 4 elements: boron, carbon, nitrogen, oxygen. Put them in order of increasing or decreasing ionization energy or electron affinity, okay? All right. Questions so far?
I have a question.
Yes, Janelle.
I actually didn't understand any of that. Okay, so how did you know? Okay, so for the affinity one, when it goes from left to right, it increases, and also
Yes.
for the other one, it increases. What
Yes.
about when it goes down for the affinity, or does it not go down?
Well, I didn't want you to necessarily worry about that one. But as you go down, here's what happens. If you're looking at, let me see, I'm pretty sure I put a periodic table somewhere. Well, here's the deal. Let me zoom in on this. As you go down, we know the layers of the onion increase, right? So let's say here's helium up here, He, and it's on row 1, so it's got a single layer, right? Single energy shell. Now I think I forget. It goes fluorine, bromine. Let's draw a picture of bromine. Bromine's on row 4. So here's bromine. 1, 2, 3, 4. Okay. Now bromine is going to have, because of the layers, okay, remember that electrons way out here versus electrons on shell 1, they don't feel the pull of the nucleus. And it's the nucleus that attracts electrons, right? That's where the positive charge is. And let's also think about it. As you go down, you increase in the number of protons in the nucleus, right? I wish I had a picture of a periodic table. Here's one. Okay. So bromine has 35 protons in its nucleus. Okay. And because of that, well, let's go with our comparison to helium. Helium has 2, right? So as you add more protons to the nucleus, you're going to have a larger pull on electrons. You're going to want electrons more, right? Does that make sense? But the data isn't as clear on, I want you to be able to look at this graph since I put it in the lecture. I don't want you to worry about this trend, okay? As you go down, you have more protons and you have a higher affinity for electrons, but you also have to think that, you have electrons on different layers, like you're building your layers as you go down, and those electrons aren't as easily felt by the pull of the nucleus. So it's a little more muddy. The ones I drew in, those are the only ones you need to know, okay? So I'm gonna erase this. I don't want y'all to worry about this. Any other questions on that? Okay. But I do want you to know these trends. I want you to know ionization energy, and I want you to know atomic radius, which we didn't draw on here, but we have that from last week, okay? As you go across atomic radius, it decreases. All right, and then as you go down, atomic radius increases. All right, so there's that. Okay, forming ions a little more. So that's electron affinity, ionization energy. And Janelle or anybody, if you have any other questions on this, don't hesitate to shoot me an email. We can talk more about it via email, or there's going to be some practice problems that may help as well clarify. Or read the textbook, okay? Because sometimes I know that maybe you don't understand the way I explain things as clearly, and the textbook is a great, it's a great another example or way to read the same material, just put into different words. Okay, now I told you guys I want you to be able to look at the periodic table and predict the charge on almost any element as what kind of ion it would be, okay? And the rule that helps us do that is called the octet rule. Sorry, guys, I'm hitting all kinds of buttons over here. The octet rule, okay? And here's what the octet rule says. It says that main group elements, pause. Main group elements. You need to know this is not all elements. This is only the main group elements. So we're not talking about transition metals here. We're just talking about the main groups. Remember last week we learned how to count main groups. Okay, move forward. Main group elements undergo reactions that leave them with how many? 8 valence electrons. Okay, so that's why it's called the octet rule. Octet indicates 8. Okay, an octagon has 8 sides, therefore we have octet rule, 8 valence electrons. So knowing that if something's going to get 8 valence electrons, you need to think, is it going to want to give away electrons? Is that the shortest route to get 8? Is that the quickest way? Or is it going to gain electrons? Does it have 6 and it only needs 2 more? Okay, things like that. So look at this top figure here with the sodium and the chlorine. We've drawn the electron dot structures for the neutral atoms. Okay, you've got 1 valence electron, 1 dot on sodium. You've got 7 on chlorine. When sodium gives up its electron, because it only has 1 valence, and we said underneath it's got a full set of 8. Now we're going to draw as an ion, and it lost the only valence that it had. So now we don't draw any. We just draw the plus sign. Chlorine found that electron, it gained it, so now we're going to draw 8 dots around chlorine. It has a new electron dot structure, 8 valence, and we put the minus sign, okay, to indicate that it's now an anion. This becomes our cation. Remember, cats have paws, cation, positive charge, anion, ants, okay? All right, think about this bottom one. I want you to do this bottom one. If element X, which by the way, what a violation. That is wrong. It should be on this side, that dot, okay? If element X has 2 valence electrons, okay? And we see those 2, and then element Y has 6. There's 6 dots on Y. How are these two going to react together? How will they trade, give, or receive electrons? What are we going to end up with so that they both have 8? What products would we get? Just the way we drew sodium and chlorine up here. What would be our products down here? So take a second, write them. Okay, Brennan says X gives 2 to Y. Do y'all agree, disagree? Anyone think anything else? So what would that look like? If X gives away both, now X does not have any dots, no electrons. And do we write a charge on X? What's the charge?
Plus. Positive.
Plus 2. Okay, plus 2. What would Y look like?
It'd have 8 electrons with a negative.
Because we had 6 and it gained 2 more, now it has 8. So here's all 8. And what kind of charge does Y now have?
Negative.
Negative 2. Okay. So you don't have to stop with just giving 1 electron. It's in fact, if you think about the main group 2 elements, calcium, magnesium, okay, if you're looking at a periodic table right here, these guys have 2 valence and they're more satisfied when they give away both of them, okay, and they end up as a plus 2. Okay, this is going to be our first poll question. So let me pull up the polls. I want you to look at this picture. Again, you don't have to worry about this stuff. Look at this. I want to know. Let me pull up the poll. Okay, here's our poll question. Which of the following identifies the atom that you see on the slide with the correct charge? As the correct ion with the correct charge. Sorry. going to give you all a minute. We only have like not even 20 people have guessed so far. Count the number of protons. Count the number of electrons. Figure out, how do you figure out what element that is? I'm going to pull the periodic table up in case you need to see it. I know it's kind of small. There's a periodic table in the front cover of your textbook as well, because you'll probably want to look at a periodic table. How do you identify an atom? By the number of its atomic number, the number of protons. Each symbol on the periodic table has the number of protons in the top corner. Does anybody ever drink like LaCroix or anything? We love carbonated waters. The first time I drank it, I will clarify, probably want to like spit it out because it has no sugar. And you think these drinks have sugar. They just look like they do. But sorry, I picked the wrong one. I meant to pick a different one. Well, that's okay. I don't see who picked what anyway. So if you picked the wrong one, that's all right. As long as you know the right one in your head. Still got like 10 people that need to respond. We're 80% voted. Vote. Voting is important, everyone. While we're talking about voting. Exercise your right. Okay, I'm about to pause it because we've been on this for 2.5 minutes. If you don't know by now, you may not know. End the poll. Okay, we got a wide range of answers here. A wide range of answers. Does it tell you which one is correct? It looks like I have 2 in different colors. Which one does it say? Does it show which one's correct to you? No? Okay. The correct one, it's got 8 protons. That means we are oxygen, okay? 8 protons. That 8 indicates 8 protons. So if you picked something with oxygen, you're in the ballpark. But we're not done there. We have 8 protons, 10 electrons. So we have a positive 8 because protons carry positive charge. Plus we have 10 negative charges. Overall, that gives us a -2. Okay, so we have a -2 charge, which makes us an anion. All right. So you should have picked E. You're oxygen with a -2 charge and you're an anion. Okay, questions, because I think we have a crazy amount of different answers here. Why did some people think cation? Don't be afraid. If you picked cation, just own it. Why did you think cation? Sometimes it trips people up when you say you're gaining electrons. You think you're gaining positive charges, but you have to remember electrons carry negative charge. So if you're gaining electrons, you're gaining negative charge. And if you're losing electrons, you're becoming more positive. You're getting rid of your negativity, right? Okay, I'm going to close that poll. We're going to move on. Here's where, if you understand the octet rule, you can look, we're gonna see how do I look at the periodic table and know which group forms what kind of charge, and if they're a cation or an anion, and then you should be able to predict it anytime. We're only going to talk about 4 of the main groups, main group 1, 2, 6, and 7. But main groups 3 and 5 also carry on the trend. The group we're not going to talk about is, that's exactly what tripped me up. Okay. The main group we're not going to talk about is main group 4. Okay. Main group 4, they have 4 valence. So do they want to give away 4 or receive 4? It's kind of the same distance either route. Well, we don't really see main group 4 elements in ionic compounds very often. They mostly participate in what we call covalent compounds. Remember at the very beginning of lecture, we said there's 2 kinds of bonds, covalent and ionic. They more so participate in covalent bonds. So we're not going to talk about group 4, but 1, 2, 6, and 7, you should be able to predict their kinds, the kind of ion they form and the charge every time. Group 1. These are our metals, except for hydrogen. Even though hydrogen's not a metal, it still has 1 valence, and it will do the same thing. It'll form the same kind of ion. So here's the electron dot structure. We got 1 valence. To have a full set of 8 underneath, unless you're hydrogen or lithium, I'll say that as well. To have a full set underneath, you're going to give away 1 electron. That's what you want to do. That's the shortest route to become stable. All right, and so these form a +1 charge. And in fact, on the exam next week, you're going to have a resources page, which will have a periodic table. And if I were you, the periodic table is going to be this one. It'll look exactly like this one. If I were you, I would go in, I would print this thing off. I'm going to post the resources page early. You can go in and print it off to have it with you if you want it as a hard copy. I would go in and I would write +1, +2, -2, -1. I want to write what we're about to do on that table for your exam. That's what I would do. Okay, so group 1A, they form cations with a +1 charge. Okay, and they give off 1 electron. So then we write their symbol like this. You would write in the elemental symbol and you'd put the plus sign by it. Group 2A, they have 2. And again, I'm sorry that they keep writing the electrons on the same side. You should write them on opposite sides. But they're going to give away both of the electrons. They're going to give away both. And when they give away 2 electrons, you end up being a cation with a +2 charge. So +2, that's what they're going to do. Form cations with a +2 charge. Okay, that's pretty straightforward. Group 6A, here's their electron dot structures. Here's 2 examples. Here's 6A. Here's 2 examples, oxygen and sulfur. 6 valence electrons, so we draw 6 dots around them. 2 have 8. They could either give up 6 or gain 2. Which one do you think sounds more favorable? Gain 2. So that's what they're going to do. They're going to gain 2. Okay. Now they're going to be an anion. If you gain electrons, you now have more electrons than you do protons. So overall, you have negative charge. Now you have 8 valence. So you're stable and you're satisfied, but you have a -2 charge. Okay. So these are going to form anions with a -2 charge. Just about every single time. It's always predictable. Okay. Group 7. These are the halogens. They have the highest electron affinity. They want an electron so bad because they're 1 away from being stable like the noble gases. So here's their electron dot symbol. We could be talking about chlorine, fluorine, bromine, iodine. They're going to gain 1 electron, and when they do, you have a full set of 8, and now you have a -1 charge. Let's do an example here. Fluorine has 9 electrons and 9 protons starting out. 9 protons, 9 electrons. So this is +9. And if we gain an electron, okay, now we have 10 electrons. So what we have is +9 plus -10. All right. And overall, we're going to have a -1 charge. You could do that with any of your halogens. Up here, oxygen. Let's go with sulfur. Sulfur's right here. Okay. Sulfur has an atomic number of 16. What does that mean? Atomic number is the number of protons. So it's got 16 protons. Starting out, it has 16 electrons. But if we gain 2, now we're going to have 18 electrons. We still have 16 protons. So we do 16 plus -18. And that is a -2. Okay? So that's how we're determining the charges on these things. And these always form a -1. All right. So again, I would come in and I would write this +1. Notice that these first 2 groups, the numbering matches the group number as well. The charge as an ion matches their group number. Over here, 6 is a -2. These elements form anions with a -2 charge. Group 7 forms anions with a -1 charge. Now, what do you think about groups 3 and 5? We haven't talked about them. What do you think happens to main group 3? They have 3 valence. To become like a noble gas, to satisfy the octet rule, they can gain 5 electrons or they can give away 3. What sounds most reasonable? To give away 3. And if you give away 3 electrons, what happens to you?
You become a cation.
Yes, with a what charge?
+3.
That's correct. Now, what about group 5? You have 5 valence electrons. You can give away 5 or you can gain 3. Yep, someone mouthed it, gain 3. Oops, so once you gain 3, you're not positively charged. You're negative charge. Okay? Questions on this? We've got about 10 minutes left, actually 9. Let's talk about transition metals for a second. Hang with me. Hopefully we'll get to a review question at the end, a review question or two here at the end. Transition metals are different. They're weird, okay? They will always lose their valence electrons first. And then sometimes they'll lose additional electrons. Now, how many valence did we say transition metals have? Anybody remember? All transition metals have 2 valence electrons starting out. 2, they all have 2 valence electrons, okay? Now, because they can sometimes lose additional electrons, they will therefore sometimes form multiple ions. And we should write cations, honestly, with unique charges. Multiple cations with unique charges. So look at this. Here's our transition metals. Some of them only have one type of ion listed in their box. Some transition metals only form one kind of ion, but some of them form multiple cations with unique charges. For example, chromium. You can have a chromium +2 or a chromium +3. Iron. You can have an iron +2 or an iron +3. Okay, the iron in our hemoglobin is an iron +2. All right. So there's a little bit about transition metals, a little bit more though. Some transition metals will always form multiple ions. Some invariably only form one kind of ion. And there's different ways we name these. In fact, we're going to spend a lot of time on Thursday naming ions and compounds. So let's look at the ones in red. The transition metals in red. These are common ions with more than one. So multiple possible charges. Okay, again, we pointed this out, but chromium, +2, +3. Cobalt can also be a +2 or a +3. Copper could be a +1 or a +2. So here you can see copper can sometimes only give away 1 valence. Another very unique thing, if some of you look closely, you'll notice mercury is weird. Let's look at mercury. You have 1 mercury atom with a +2 charge, or I should say ion. And then here you have a mercury 2. So there's actually 2 mercury atoms here. And overall, that one has a +2 charge. That's not a typo. Here it's 2 atoms and each mercury atom has a +1. So overall there's 2 +1 charges. And sometimes we call it mercury 1. Oh, one thing I forgot to mention, if you look back up here, because, for example, with cobalt, right here, we can have a +2 or +3. We have to have a different way for naming these that we understand which ion we're talking about. So therefore we use Roman numerals, okay? So if I'm talking about cobalt +2, I'll just write it in Roman numerals, cobalt 2. If I'm talking about the +3 cation, I'll write cobalt Roman numerals 3 to indicate the charge. So any box that's red and there's multiple kinds of ions, you have to use Roman numerals like this. Anything that's blue, for example, silver, only ever forms a +1, okay? So I don't need to use Roman numerals, because if I just say silver, I know it's a +1 because it only forms one kind of cation, okay? Okay, so in blue are other transition metals that invariably have one charge. They only form one charge. Therefore, it's okay to omit Roman numerals when you name those. Questions on the transition metals? Okay. All right, we're done with introducing new content. I want to see how well did you grasp this. So the next 2 or 3 minutes, just hang with me. Let's look at I got a couple poll questions, and when we hit time, we'll be done. Okay, here's our poll question. According to the octet rule, how many electrons must an aluminum atom, Z13, what does Z mean? Here's a periodic table if you need one. How many electrons would it either gain or lose to attain 8 valence electrons? Think about what main group it's in. Therefore, how many valence electrons does it have? And would it want to gain or lose, depending on that, how many to get a full set of 8? So here's aluminum right here. Z equals 13, that's the atomic number. We're only 50% voted. I'm gonna call it though, in poll. So the highest chosen response was that it would lose 3, and this is correct. Okay. Why? If it's in main group 3, which it is, if you count the main groups, here's main group 1, here's main group 2, skip the transition metals, here's 3. That means it has 3 valence electrons. So it can either gain 5 or lose 3. And the easiest, shortest route, the thing it's going to do is it's going to lose 3 and form a cation with a +3 charge. And in fact, if you scroll up, that's what you see right here. Okay, on that chart. Okay, let's see. Let's go to the next question. This is the last one, and then we're done. The only thing is there's like 4 questions in this one. So I want you to answer all 4. It should be quick. You're only choosing between 2 elements. First one, which of the following elements has a lower ionization energy? Go find your trend that we drew. Look at their placement. It's either beryllium, Be, or boron, which is just B. In other words, which element will lose an electron more easily? Based on the trend we drew in ionization energy, which one has lower? Okay, that's number 1. Number 2, which of the following elements has a lower ionization energy? In other words, which element will lose an electron more easily? Okay, so same idea here, but we're picking either S or Se, sulfur or selenium. I realized I meant to edit my questions so that we asked one question that was which one was higher and then the other which one was lower, and I forgot, but that's okay. Answer it the way it's written. Okay, it's time. So here's the deal. If you haven't voted yet, I'm going to end the poll so that we talk through these real quick and you get answers. A lot of you are still voting, but I don't want to go over on time. So let's end the poll. And let's look at these really quick. Where's my periodic table? That's what we want to look at. I'm going to turn this sideways. Okay. So ionization energy. As you go from left to right, we said ionization energy. What happens to it? Does it increase or decrease?
Increase.
Increase. So what was our answer here? Whichever one It says which one has a lower, okay? So whichever one is further to the, what's this? This is my left. Whichever one's furthest to the left, okay? That's the one that has the lower ionization energy. So you're either looking at beryllium or boron. Which one's further to the left? Ionization?
Beryllium.
Beryllium. Okay, so you should have picked the beryllium, but it increases as you go from left to right. So beryllium has a lower ionization energy. Group 1 has the lowest. Okay, what about sulfur and selenium? Sulfur and selenium. Okay, what happens to ionization energy as you go down the periodic table? Does it increase or decrease?
Increases.
Increases as you go down. Right? Whoop, sorry. As you go down, you're adding a layer, so the ionization energy, I thought we said it decreases as you go down. Where's our trend? Where's our picture that we drew? Yeah, as you go down, it decreases. Okay, so whichever one's further south, that's selenium, I believe. That's the one that will have the lower ionization energy. Okay, so there's selenium. Okay, which of the following elements has a higher electron affinity? Whichever one's closest to the halogens, right? So nitrogen, oxygen, you should have picked oxygen. Okay, electron affinity increases as you go across. All right, and then sodium or silicon, right here, silicon or sodium, whichever one's closest to the halogens has a higher electron affinity as well, and that's going to be Si. So, okay, that's the end of the polls. That's the end of the lecture. If there's any questions, I'll stick around. We're already over time. Thanks for joining today. I'll see you guys on Thursday.